Have you ever stopped to wonder why a ball drops to the ground, but a satellite just keeps on circling the Earth? Or how in the world a rocket can push itself forward in the total emptiness of space? Well, it all comes down to a fundamental rulebook for motion, one that was written over 300 years ago. And today, we're going to open it up.
So what is this grand set of rules? You'd think it would be impossibly complicated, right? I mean, it governs everything. But the answer is actually surprisingly simple. We're about to break down 3 powerful laws that are the bedrock of what scientists call classical mechanics.
And this is the guy who wrote the book, literally, Isaac Newton. Back in 1687, he published his masterpiece, the Principia Mathematics, and it just changed everything. He wasn't just guessing how the universe worked. As he says right here, he didn't feign hypotheses. He looked at real-world stuff, phenomena, and worked backwards to figure out the rules. He built a system that could predict pretty much everything, from a falling apple to an orbiting planet. All right, let's jump into the first rule. I kind of like to call this one the law of the lazy universe. It basically describes the default state of, well, everything. So this is Newton's first law, and you'll often hear it called the principle of inertia. The official language is a bit dense, but what it's really saying is that objects have this built-in resistance to any kind of change in how they're moving. Let's put it even more simply. Things just keep on doing what they're already doing. If something is sitting still, it wants to keep sitting still. If it's moving, it wants to keep moving in a perfectly straight line at the same speed. You can really think of it as a kind of cosmic laziness. It takes efforts, a force, to make anything change. Okay, so Law 1 is all about what happens when there's no force acting on something. Law 2 is where it gets really interesting. This is the rule for what happens when a force is applied. This is where things really start moving. And there it is. Probably the most famous equation in all of physics. Force equals mass times acceleration. F equals ma. This tiny little formula is so powerful because it connects 3 huge concepts. It tells us that if you want to make something accelerate, the amount of force you need is directly tied to how much stuff, or mass, it has. More mass, you're going to need a lot more force to get it moving. Now, this little diagram points out something absolutely crucial. Force and acceleration are what we call vectors. Don't let the word scare you. It just means they have a direction. The direction you push is the direction the object accelerates. Simple as that. You push harder, you get more acceleration. It's a relationship that just makes sense. But, F equals m is way more than just a neat idea on a chalkboard. It is a testable, verifiable fact about how our universe is put together. So how do we take this idea from the 1600s and prove that it's actually true in a lab today? And really, that's the most important question in all of science, isn't it? It's one thing to write down a cool equation, but how do you prove it describes reality? Well, scientists have come up with a really clever experiment to test every single part of Newton's second law. And this is basically what it looks like. To really isolate the different pieces of the puzzle, they use a super low friction track. The whole point is to prove that the formula isn't just a theory, it's a fundamental truth about our physical world. The setup is actually beautiful in its simplicity. So first, a hanging weight gives you a constant known force. That's our F. Second, that force pulls a little cart that has a specific known mass. That's our M. And third, these incredibly fast electronic timers called photogates measure exactly how fast the cart accelerates. That's our A. So you have the cause, that little hanging weight, and you have the effect, a super precise number on a digital screen. But the real magic is that scientists can run this experiment over and over, changing the force or changing the mass, and they confirm that the relationship F equals m holds up every single time. It's called a law for a very good reason. Okay, so we've covered inertia and F equals ma. Now we get to Law 3, which is incredibly powerful, super profound, and it's the source of a giant misconception that trips up just about everyone. So in Newton's own words, to every action there is always opposed an equal reaction. What this means is that forces are never lonely. They always, and I mean always, come in pairs. Take a look at this. If Object 1 pushes on Object 2 with some amount of force, Object 2 automatically pushes back on Object 1 with the exact same amount of force, just in the opposite direction. Always equal, always opposite. We call this the action-reaction pair. And this is the paradox. If you push on a wall, and the wall pushes back on you with the exact same force, how does anything ever move? Shouldn't those forces just cancel each other out, leaving everything stuck in place? This is the great misconception.
And here it is, the answer. The whole secret is that the action and reaction forces never cancel out because they act on different objects. Think about it. When you push a box, your pushing force is on the box. The box's reaction force is on you. To figure out if the box moves, you only care about the forces acting on the box. You can't cancel a force on the box with a force on your hand. Once you get that, everything clicks into place.
So there you have it. Those are the 3 laws. And when you put them all together, they create this amazing, complete system for describing and predicting how things move in our day-to-day world. So let's recap the rulebook one last time. Law 1. Objects are lazy. They have inertia. Law 2. If you want to change their motion, you need to apply a force, and F equals ma tells you how much. And Law 3. Every single force is just one half of a pair, an action and a reaction.
These laws are unbelievably powerful. I mean, we use them to build bridges, fly airplanes, and even send robots to other planets. But they do have their limits. What happens when you start moving close to the speed of light? Or when you zoom all the way down into the bizarre world of tiny atoms? Well, that's where Newton's rulebook ends, and the incredible story of modern physics begins.